Welcome to the week 8 of our Calculus 2 course. This week, while learning complex numbers, we will need to recall information related to unit circles and trigonometric functions. So today, we will do a short review of the unit circles and how trigonometric functions relate to them. Any point on the xy plane can be given using the two values, the coordinate x and coordinate y. A unit circle shows all the points that are exactly 1 unit away from the origin. We're actually looking at a triangle where one leg is equal to x and the other leg is equal to y. Let's assign an angle between the positive direction of x-axis and the array that contains point with the coordinates xy as an angle theta. So here we have a right triangle with two legs equal x and y correspondingly, and the hypotenuse equals to 1. Pythagorean theorem says that x squared plus y squared is equal to 1 squared. This gives us equation of a circle centered at the origin with right equals to 1. We also know the definition of trigonometric functions such as cosine and sine. In our right triangle, the side opposite to angle theta is y, the adjacent side to angle theta is x, and the hypotenuse is equal to 1. By definition, cosine of theta is equal to the ratio of adjacent side to hypotenuse. Since adjacent side is equal to x and hypotenuse is 1, we get an equation x equals to cosine theta. By definition, sine of theta is an opposite side divided by hypotenuse. We get an equation sine of theta equals to y. So now we know that on the unit circle, a point with coordinates x, y carries on information about cosine of theta and sine of theta, where theta is an angle between positive direction of x and the ray that contains a point xy. There are some very common useful angles of theta for which we expected to remember the values of the cosine and the sine. When the angle theta is equal to 0, this corresponds to the point with the xy coordinates equal to 1, 0. The other useful angles are pi over 6, pi over 4, pi over 3, pi over 2, pi, 3 pi over 2, and 2 pi. When we are looking at the angle pi over 6, we can immediately estimate the value for the sine of pi over 6 by realizing that the y value is about halfway between 0 and 1. In the triangle where one leg is equal to 1/2 and the hypotenuse is equal to 1, we can use Pythagorean theorem to show that the other leg is equal to square root of hypotenuse squared minus known leg squared, which leads us to square root of 3 over 2. Square root of 3 over 2 is equal to the cosine of pi over 6. In the right triangle, if one of the two remaining angles is equal to pi over 4, the other angle must also be pi over 4, or 45 degrees. Since this is an isosceles triangle, then y would be equal to x. Using Pythagorean theorem, we can show that 2x squared must be equal to 1. Therefore, x should be equal to square root of 2 over 2. Both cosine of pi over 4 and sine pi over 4 is equal to square root of 2 over 2. Let's move along to the angle pi over 3. Notice that in the right triangle where theta is equal to pi over 3, the x-coordinate of the point on the unit circle is equal to 1/2. This means that the other leg is going to be equal to square root of 3 over 2. We already looked at this triangle when we considered angle equals to pi over 6. This is when we discovered that the side adjacent to the angle pi over 6 has length equal to square root of 3 over 2, and the opposite side to pi over 6 is always equal to 1/2, which is the same information that we're using now for the angle pi over 3. For the angle pi over 3, the opposite side will have a length square root of 3 over 2, and adjacent side will have a length equal to 1/2. Angle theta equal to pi over 2 corresponds to 90-degree angle, and the point has x-coordinate equal to 0 and y-coordinate equals to 1, which means that cosine of pi over 2 is equal to 0 and sine of pi over 2 is equal to 1. The remaining 3 points are also very easy to determine x and y coordinates for. When angle theta corresponds to pi, it means that we have the point with the xy coordinates equals to -1, 0, which means that cosine of pi is equal to -1, while sine of pi is equal to 0. When theta is equal to 3 pi over 2, we have a point on the unit circle with the xy coordinate equal to 0, -1. This means that cosine of 3 pi over 2 is equal to 0, while sine of 3 pi over 2 is equal to -1. When theta is equal to 2 pi, we went a full revolution around the unit circle, and now we're standing at the point with the xy coordinates equal to 1, 0, which means that cosine of 2 pi is equal to 1, while sine of 2 pi is equal to 0. So why sine and cosine for 0, 2 pi, pi, and 3 pi over 2 are very easy to understand and remember. Remembering sine and cosine for pi over 6, pi over 4, and pi over 3 not always easy. Well, let me share the trick. Notice how the values of sine of theta are increasing as theta is changing from 0 to pi over 6 to pi over 4 to pi over 3. Well, at 0, the sine of theta is equal to 0, so this is easy to remember. But every next sign looks like the square root of either 1 over 2 or square root of 2 over 2 or square root of 3 over 2. So as we go from 0 to pi over 6 to pi over 4 to pi over 3, our numerator changing from 0 to 1 to 2 to 3 underneath of the square root. As we are rotating through the first quadrant, we stop when we hit pi over 2. And at pi over 2, the sign is equal to 1, which is, not surprisingly, the same thing as square root of 4 over 2. Value of the x-coordinate, which corresponds to cosine theta, equal to 0 at pi over 2. And as we're moving from pi over 2 clockwise, hitting pi over 3, pi over 4, pi over 6, 0, our cosine increases from 0 gradually to 1, going through exactly the same pattern. Square root of 1 over 2, square root of 2 over 2, square root of 3 over 2, and then square root of 4 over 2, which is the same thing as 2 over 2, which is the same thing as 1. I hope this little trick will help you to quickly recall the sine and the cosine values for a common angle theta. We mostly worked in the quadrant 1, but what about other quadrants? The common triangles used in the other quadrants are going to be identical to the ones we used in quadrant 1. The only difference is whether the x-coordinate would be positive or negative for that particular triangle. So in quadrant 2, all x-coordinates would be negative, but y-coordinates of the point would be positive. Here's an example of an angle 5 pi over 6. Notice how the y-coordinate is equal to 1/2, which means that the other leg is going to be equal to square root of 3 over 2. But since x-coordinate is negative, then cosine of 5 pi over 6 is equal to negative square root of 3 over 2, while sine of 5 pi over 6 is equal to a positive 1/2. Let's say we build an isosceles triangle in the unit circle in the quadrant 3, which means that those angles are equal to 45 degrees, or pi over 4, which means that our angle theta is equal to pi plus pi over 4. We know that the cosine and sine of pi over 4 is equal square root of 2 over 2. But what is cosine and sine of 5 pi over 4? The magnitude is equal to the same value, square root of 2 over 2. But because both x and y coordinates have negative values, we'll put the negative signs in front of the square root of 2 over 2. So cosine of 5 pi over 4 and sine of 5 pi over 4 are equal to minus square root of 2 over 2. Let's consider negative angle theta. Say angle theta equals to minus pi over 3. This is the same angle as theta equals to 2 pi without pi over 3. This is 5 pi over 3. We can see that the cosine of 5 pi over 3, cosine of minus pi over 3, are going to be equal to positive 1/2 because this is the x-coordinate of the point on the unit circle. In this triangle with the angles 30 degrees and 60 degrees, pi over 6 and pi over 3, if one leg is equal to 1 over 2, hypotenuse is 1, the other leg has to be equal by length, square root of 3 over 2. However, this point lays in a fourth quadrant, and all points in a fourth quadrant have y coordinates that are negative. Therefore, sine of 5 pi over 3 equal to negative square root of 3 over 2. I hope that you have found this review of unit circle and trigonometric functions sine and cosine useful. Until next time.